So let's have a molecular view of how kinase inhibitors work. In general, they all target the same site, which is common to all the kinases, and that's the ATP binding site. This is how ATP binds to a certain kinase, which is implicated in cancer. So we have, hydrogen bonds to the backbone here. Oops, right? And also an additional hydrogen bond possible here with this alcohol moiety. So it was a bit of a surprise when the X-ray structure of the kinase in complex with Tarceva was solved, because turns out that not all the interactions that had been predicted computationally were active, and also there was the surprise of this water molecule that mediated hydrogen bonding to the inhibitor. And we can see here in more detail how binding of Tarceva to the kinase is very different from binding of ATP. And that basically goes to show that there's only so much we can do in terms of predicting docking. Now that we have the crystal structure, though, it's possible to think about design analogs that will exploit more of the interactions with the ATP binding site. Another reason why it's important to explore all the possible structures that could combine in this pocket is because resistance can evolve in chronic myeloid leukemia, for example, by changing the pocket, the ATP binding pocket. Let's look at another one of these kinase inhibitors, IRESA, which was approved by FDA about 15 years ago, but it was already in the market in Japan, where it was actually considered to be way more active against cancer than it was found to be here. And it was found that the efficacy was not correlated with expression levels of the phosphorylation state, and so that therefore there was not an inherent reason for why only 10% of the patients responded. When they do respond, the effect is dramatic, and so in responders, IRESA, prolongs life by several months. And so initial studies basically had shown that Japanese patients were about 3 times more likely than Americans to respond to the treatment. And also, what it was found is that in these non-small cell lung tumors, there were somatic mutations, and that was searched. And what they found is that patients that that responded to the treatment had these EGFR mutations in the regions tested. So the next question was, do these mutations confer sensitivity to IRESA? And so they sequenced, the kinase domain of the responders versus non-responders. And what it was found that the non-responders did not have these mutations, whereas all 5 responders have this particular mutation in the EGF receptors. So let's look at a little bit more in detail what was going on. All the mutations are part of the ATP binding pocket, or alter the catalytic cleft at the surface of the catalytic domains. They basically what we find here is these 2 mutations specifically, and responders have mutations in other parts, which basically resulted in activation, making basically them insensitive to the kinase. So patients that are sensitive to the kinase inhibitors again have these 2 specific mutations, whereas non-responders have mutations in different parts of the molecules. And so these mutations actually in non-responders lead to constitutively active EGFR. So let's look at the kinase domain. And basically the so-called activation loop, that's the position where we have the mutation in most of the patients, that the responders. So this is L to R, where R is arginine in this position. So what we found here is that the knowledge of the exact mutation, or basically sequencing of the tumor of the patient, allows us to distinguish responders from non-responders, and allows us to start thinking of a therapy in a targeted manner.